So let's continue. So we said that they build them bigger and bigger to save on the economics of building those things. And once you had this big, enormous wind turbine, 4 megawatt, and you put it in Tulsa, Oklahoma, in downtown, will it generate 4 megawatt all the time, or some of the time, or never? So that involve the site statistics. So it's not just like I got a wind turbine that's 2 megawatt, give me my 2 megawatt. The question is, when does it generate that 2 megawatt? What velocity does it need to make it run? So that velocity is called the rated velocity. Okay? And when you give it the rated velocity, it will give you the rated power. So when they sell you the 2 megawatt wind turbine, they will tell you this is rated for, say, 10 meter per second. You give us 10 meter per second, we will give you the 2 megawatt. You give us 7 meter per second, and we'll give you less. There is a power curve that we will see. Okay? So that power curve will, and actually let me jump to the power curve. It's important to see it before we go further. So here is 300 kilowatt turbine, and here is 7 megawatt turbine. Okay, and so this guy have this power curve. Let's open this up a little bit. Ouch. This 7 megawatt wind turbine will give you the 7 megawatt wind turbine only when the velocity is 16 meter per second or higher. When you are 16 meter per second or higher, you will get the 7.5 megawatt. If the velocity is, I guess, what do you call this? 2? Let's call this 2 meter per second. If the velocity is 2 meter per second, the power coming out from the generator is how much? 0. And the CB at this moment is, the CB is power output over power input. The power input is half rho A, and you can see the A is huge. Rho is 1.2 for air. A is the pi r square, and what is the R? This plate is, rotor diameter is 127 meter. The diameter is 127 meter. Okay, so pi over 4 d square, it's pi over 4 multiplied by 127 square. Okay, so we got huge power input even at 2 meter per second, but the power output is 0, and therefore the CB is 0. The CB is 0. This is the CP. So the CB is 0 when you don't have power, and as the power starts to ramp up, the CB will rise very quickly to hit what? What is the scale? 0.49. Remember the chart we had at the beginning of the course? You hit what? You hit help. Not that's limit 0.59. You will hit this point. You will hit this 0.49. Right, for 3 plates. So they managed to hit that 0.49 very quickly. They hit it here, right? Sorry for that. So they end up hitting it over here. So they got 0.49. And so the wind now start to go from 5 to 10, and they are maintaining 0.49, and the power is getting higher and higher and higher. And then once the power hit, or even before it hit that point, but once the power here is the rated power, and the wind is like 60 meter per second, what happens if the wind go to 20 meter per second? The half rho AV cube, the input power is more and more between 15 and 20. But can I generate more than the 7.5 megawatt? Can I generate more than my rated power? No, I can't, right? Can my 450 horsepower car, if I keep hitting the gas more and more, can it get more than the 450 horsepower, whatever? Yeah, unfortunately not, right? Because the whole thing will break apart, right? If you deliver that more power. Can I put nitro whatever in the engine and no, the thing will explode, right? So the generator, the gearbox, the wires, the cable, everything is designed for that rated power. Okay? So what happened then if I hit my rated power at 60 meters per second, but there is more and more wind? What do I do? What should I do? What would you do? You change the angle of attack of the plate so that you make the plate suck on purpose, right? So that plate, that angle, maybe it shouldn't be optimal. Maybe we shouldn't really get the maximum lift. Maybe we should start making him not really performing that well. Why? Because we don't want him to get all the power available to him. Because if he does, he will go beyond the rated power. Okay? So by this control of the plate, you can basically start making him suck on purpose, right? So his CP will start dropping. Okay? So that he maintain what? He maintain the power cap. Okay? So this is the output curve, and this is basically the CP. When you hit the maximum power, the rated power, this would be the rated velocity, rated speed when you hit the rated power. And the moment you start be online and people can put like a lamp on your output, that is the cut-in speed when you are allowed to produce power. And once you hit 25 meters per second and the plate is already stalled and you cannot get any more like than this, and the velocity is really too much for you anyway, you shut down the turbine, and that would be the cut out velocity. So you have cut in, you have rated, and you have cut out. Okay, you don't deliver anything at the output, and you don't deliver anything less than cut in. Okay, so now the site. So if I buy this turbine, and we pay all our money to buy this turbine, and you put it in Tulsa, Oklahoma, we better see then what is the statistics of the wind in Tulsa, Oklahoma. How many days, how many hours per year? How many hours per year do we get velocity at what? What's the rated velocity here? I would say maybe what, 12? Maybe 13 something? 13, let's call it 13. So 13 or higher, that's when we get the rated power. So how many hours per year we get 13 meters per second or above? So 8,760 hours per year. So if we get 4,000 hours per year that we are at rated or higher, those are, you multiply this by the megawatt, the 4 megawatt, 7.5 megawatt, and that would be, multiply the hour times the megawatt, what do I get? I get the megawatt hour. I get the energy. It's like the kilowatt hour, but in megawatt hour. Okay? So each kilowatt hour, how much do we pay for roughly in Oklahoma? 11 cents. That's a good number. So for every kilowatt hour, we pay 11 cents. Right? So if you are the company that's running this one, you know that you will end up, whatever megawatt hour you have, multiply this by 1,000 so that you can get the kilowatt hour, and then multiply by 11 cents, and that's how much money you are generating from that turbine. Okay? I'm saying, well, how many years does it take to pay back the turbine? You will get it from that calculation. You figure out how much money you make from that turbine per year, and you will say neglect maintenance and like this thing is running for free basically. but that's the minimum number of years that you will get your money back. How much output you get, megawatt, time the hour where it will maintain that megawatt, time the price per unit that you are selling. Okay, so this is from the manufacturer, right? But we need to couple this curve with the site. In the homework, we basically need to figure out, if I give you a turbine like this in a site with certain statistics, how much we'll actually get from it. Okay, so to do this calculation, we need to understand the statistics of the site. Okay, and they do this by table like this. So what in that table? They divide the velocity into basically bins, so from 0 to 1, from 1 to 2, from 2 to 3, and then in that wind category, how many hours per year did the wind blow in this place? Okay, so 80 hours per year, the velocity is 0. How much power you will get for that 80 hours? Nothing, 0. 204 hours per year, the velocity is from 0 to 1. If we buy that wind turbine, the 7.5 megawatt turbine that has a cut-in speed, we decided from this graph that is going to be 2 meters per second. How many power do I get from this 204 hour? Cut-in speed 2 meters per second. And from 0 to 1, it's 204 hours. How much power do I get from it? 0. Why 0? Because that velocity is lower than the cut-in speed. I mean, this thing is not even rotating, right? From 1 to 2, 400 hours. How much power do I get? 0. The cut speed is 2. Now, from 2 to 3, there is 800 hours per year. The velocity is 2 to 3. Very good. So this is V rated, and this is the V cut out. V cut out, and this is V cut in. And on the other side, this is the power. Okay. So what you need to do on this graph is to basically read those numbers to the best of your eye can do. You will get those numbers. Okay. So once the velocity hit, let's call this 15 and let's call this 3. If the velocity is 15 or higher, you get 0 power. If the velocity is 3 or lower, you get 0 power. If the velocity is 4 or 5 or 6, you get how much? You get this number that you are reading from here. Okay, so let's assume that at 6 meters per second, the velocity, the power over here is, say, let's call it 750 kilowatt. Okay, and so in that velocity, he said there is 850 hours per year. The velocity is going to be 6. So how much energy I'm going to get from that velocity when I use that turbine? So the energy is going to be the B out multiplied by the hours for that category, and you add all the velocity pins. So from I0 to N. So what I'm saying is that you go to every velocity, 0 velocity, 1 meter per second velocity, 2 meter per second velocity, 3 meter per second velocity. You multiply the hour that the velocity stay in that range time the bar output from the graph. And so at the end, you will get, if you write this in kilowatt and this is an hour, you will get the total kilowatt hour. Okay, that is the energy output, kilowatt hour per year, because this hour is basically hour per year, so you get the kilowatt hour per year. So now if you would like to figure out how much dollars output that you get, you multiply the kilowatt hour per year time the dollar per kilowatt hour. Okay, and we said this is for Oklahoma, it's like 11 cents. Okay, and that would be the dollar output. Does this make sense? Very good. So they do this using table like this, hour per year, and they basically figure out how much power. But it would be nicer rather than the table if we have a function that describe that site for us. Then we can do that optimization very easily rather than just like discrete numbers. And so they look to this, look at this. This is the bin number, with the bin number corresponding to certain velocity. So bin 14 is like when the velocity is 12 to 13, and they can write either the hours per year, or if you divide the hours per bin divided by the total hour per year, you get what percentage. So if I divide 800 hour over 8,760, I will get, it's 9% of the year you stay here, and so you get probability distribution function. So they try to look to this curve and they try to come up with a function that describes this curve. Does this curve look Gaussian to you? No. What's a Gaussian curve look like? The bell-shaped curve, right? That's the Gaussian. That's not Gaussian. So they say, we cannot describe wind energy by Gaussian curve, unfortunately. That would have been so cool, but we can. So they figure out this is the curve for wind energy. They said that the Weibull distribution is really the way to describe the wind turbine statistics, where on the x-axis you had the velocity or the velocity bends, and on the y-axis you have either the hours or the percentage of the year where the wind stayed there. Okay, so that it looked like Gaussian, but it's not. I mean, that's not exactly Gaussian function, but it looked similar. But it allows you to have this long tail, and it allows you to have actually the shape of the curve depending on that K and the C. Okay, so the K is the shape parameter and C is the scale parameter. So playing with the C make you go to higher velocity, and playing with the K you make the curve either spiky or a little bit diffuse. So with the K and C in their hand, they can go to any site and say, for Tulsa, Oklahoma, K is 2 and C is 7, for example. Okay, I'm not saying it's 2 and 7. I'm just saying any number. So they adjust this thing, and they can fit the data they get from different cities. Okay, and they have the function. So K equal 2 is popular, and when K equal 2, that become another distribution that I'm going to show you. But here is how the K look like. So K3 very spiky, K2 a little bit more diffuse, K1 is like spread everywhere. Alright? And this is the probability distribution function for any K and C. Now if you play with the C bigger and bigger, C10, C15, C20, you see is moving the C toward the higher and higher value. So this basically, the site will have more velocity in the maximum. But it just that happen in the wind energy, it's never like just a spike. It's not like we only have wind is blowing in this place almost 40 meters per second. Anytime you come out, it's 40 meters per second. Usually you will have the curve to it. Right? So when a special shape of the Weibull distribution is the Rayleigh distribution. Okay, and so its function is basically this. Okay, where x is the velocity and that is the distribution function. So what do they do with those distribution functions? How good it is. Well, if you have an equation for that h, that distribution function, you have the equation for it, rather than what we did here, and we basically end up making, you will end up making a table. If you don't have a function, what you will do is you will do the I, you will do the VI, you will do the hour I, and you will do the power output I, and then so this you will get, here is bin 1, 2, 3, 4, and that is for velocity, like 5, this is 10 meters per second, this is 15. So we are making our bin every 5, not every 1. Of course, there is advantage of making it super fine so that you can get the smooth distribution. But and so here it's like 40 hours, and here it's 200 hours, and here it's 800 hours, and here it's like 100 hours, and the bar output based on this graph. When you find those points from the graph, you'd say, well, here the bar is 0, and here the bar is 50. This is in kilowatt, so it's a small turbine, and here it's 100, and here it's 100 kilowatt hour, and then after that it's 0, because this is a cutout speed. So I'd say at 25. So then it doesn't really matter how much hour you spend. And to come up with the energy, it's what? Sigma Bi, the power multiplied by Hi. This is the energy out. Right? And you have to multiply this times this times this, 10. So rather than doing this summation of the H times the P, if you have the equation, you will simply just do the integration. Okay? And that's what they are trying to come up over here with. So to come up with the energy extracted, he's still trying to multiply the hour time the power available. Okay, but he's doing it by integration. Okay, this is the energy available, by the way. So let's look at this. So anyway, in order to come up, if you have the distribution function of anything, wind speed, students' grades in an exam, if you have the function and you would like to find out the average, the mean, you do what? You multiply that distribution function times v and you integrate from 0 to infinity. Okay, any distribution function of anything, if you want the average of that thing, that's the way to do it. Okay, so interesting. If I want also the average of, do I care about the average of v or do I care about the average of v cube? I care about the average of v cube because the wind energy is not half rho AV, it's half rho A V cube. So I really care about V cube in that site to figure out whether that site is gonna be good for my company and we will get our money back or not. Don't tell me what's your average velocity, tell me what's your average V cube. Right? Because I multiply this by the CP, hopefully it's gonna be 0.49 maximum efficiency ever. I multiply that average available energy by 0.49 and that will tell me the power output that I'm gonna get from my wind turbine in that place. Right? And multiply this by 11 cents and that will tell me how much money I will get. So the average half rho V cube, you still multiply by the probability of V and you integrate. Okay? And so a very good question right now is, what is a good question for a free quiz? I'm telling you the average velocity is hv times v and the average power would be hv times half rho v cube and you integrate. What is a good question to be asked right now? Well, no, the area, think area is here, but he's basically taking the area out of the integration. So he's saying the power per area. So you make the turbine bigger and bigger, you get more and more. So he's just like doing it specific power. No, the good question would be, why do you even do this? Didn't you just get your V mean? If you have V mean why don't you just multiply half rho AV mean cube and get the average power? And here is what's weird. The average of V cube is not the cube of V average. The average of V square is not the square of V average, okay? So if I want to get the power, the average power, it's not half rho V average cube. This is different. This velocity is basically, he's telling you, you have to do this integration. And so if you do this integration and take the cubic root, this would be called VRMC, right? So point is, if you want the average power, you have to do this integration, or if you have a table, you do the summation. You cannot just use the average velocity and cube it. Okay? Does this make sense? Just try make any distribution and try to come up with the average velocity and cube it, and then try to come up with the average V cube, and you will see it's different. Alright? So if CB is 0.5, and we said 0.49 is more like it, but assume 0.5, then the power extracted would be half of what is available. And so he's saying, well, the power extracted then would be quart 1/4 rho AV cube. Okay, that's the available power. So the energy, the joules, this is just in megawatt. This is what's available in megawatt. To multiply this by joules, to turn this into joules, we need to multiply by the hours. And how many hours does the velocity stay in each category? It's the HV. So that big table that we made on the slide, tabulating all the hours and multiplying the hour by the power output and adding all of them to come up with how much total kilowatt hour, they can do it with one integration, because that HV is the hour division. That distribution function is how many, what's the percentage? It stays from 0 to 1 and 1 to 2 and 2 to 3 and 3 to 4 all the way to infinity. So multiplying that HV, which is kind of percentage to fraction, times the total 8760, that would be the hour, times the V cube, that is the power output. It's not V cube, it's the quarter, because he's assuming basically CB 0.5. So this slide basically trying to tell you that if you have the function of HV, you'll be able to calculate the power output immediately from the integration. Does this make sense? And so here's an example basically. Okay, so he's saying we have a Weibull function with K 1.5 and C 15. So it would look like this if you plot it. And by the way, this number over here, so that you will not be tempted to grab this number and think that is V mean. That's not the mean, right? That is the moon, right? This is the maximum or the most probable velocity. Like it happened a lot. So that's the mood. Some distribution, not wind energy, but some distribution will have two moods. We call them bimodal. So they have mood like go up and then go down and go up again. And you are tracking two different phenomena, for example. Okay? But anyway, that's the mood. Huh? And so he is plotting the distribution. Here's the different velocity that he will have, and on the y-axis, this is basically the number of hours per year that the velocity will stay in that range. Okay, and again, knowing K and C will replace that graph in the equation. Okay, so find the mood. That's the mood. Find the VRMC. What's VRMC? That is the average of V cube, and you take the cubic root of it. Okay, he wants you to do this integration, because if you have that velocity, then that is the average power available. You multiply by the CB, that's the max, that's the power gonna output power. You multiply it by HV and you integrate, you get the energy. Okay, so he wants you to calculate the VRMC, and he wants you to calculate the power extracted per meter square. So again, the power per unit area, what Jairo was asking about. So he wants you to do it like this. Okay, so this is a Weibull function. Okay, and multiply by V, integrate, that's the V mean. Multiply by V cube and integrate, and taking the cubic root, that is VRMC. Okay? And to get the energy output, you will do this. Alright? So this is the energy output that he put after he did the integration. It will be like this. And that show us that at the maximum velocity, when the velocity really go high, there are usually not that many hours where the velocity get that high. So designing a turbine that will go that far will require probably a lot of material and a lot of control, and there's not that many dollars in that area anyway. So that's why they did basically make a cut out velocity. They say, well, it's not really make money by going that far, right? So the control that they do is basically will end up resulting in those two limits, the cut out velocity and the cut in velocity. Okay, so he's saying if we plot the half rho AV cube, just the available power as function of wind speed, we will end up with something like this. This is the V cube curve. You know how y equal x squared look like this, and y equal x cube will end up going even higher. So if we basically just harvest everything available, it would be like this. Of course, multiply by a CP. So half rho AV cube, that's the input power, multiply by CP, and that would be the output power. But you on purpose basically cap it once you hit the rated power and say, no, I'm not going to get any more than this. And after you cap it, you even shut it down at the cutout speed. Right? And so that's why the CP will probably be really, really good in this range, but then at this point, in this graph, the CB will start dropping, and then at this point, after this point, the CB would be how much after you hit the cutout speed? The CB would be 0. You will not get anything after the cutout speed, right? That's why the CB basically will drop 0. And actually, before even you hit this place, the CB will slowly drop from you. Okay? So this graph is also this table. See the wind and the power CP. So you take this table and you put it to your site next to the site. So what we need is one column for the hours from the site, and then you'll be able to calculate the output power, output energy too. Okay, make sense? And so he's saying that the wind could be coming like this. Of course it will fluctuate like this, but the output power will be constant. Once you hit the rated velocity, you will be constant. And so who's absorbing all those? The plates is doing that, right? And the generator could also play with the torque in order to maintain the right velocity of the rotor. Okay, so there's a lot of control over it. The blade will change the pitch angle so that you can purposely lower down your output. So even if the input is higher and higher, you say, no, I don't wanna. And you slow you in purpose basically spoil the curve. It's the angle, right? It's the pitch control, right? So one should expect a CB curve to look like this, right? He would rise, maintain a constant, and then drop to a 0. And so this is in this example over here. So here is basically the curve of the turbine. This is a 7.5 kilowatt per meter square. So whatever the meter square of that area, you multiply it by 7.5 kilowatt and you will get the bar output. Okay. And so what does he want from us? calculate. So he said this wind turbine have a cut-in speed of 5 meters per second. You can see that here. A cut-out speed of 35, right? And the rated is probably what, 29 or something at this point. And the maximum power coefficient is 0.5. We don't see that over here, but if you divide the output power over the input power, you'll get 0.5. Determine and plot the following: the power density of the system, the CB versus wind speed, and the energy extraction, and the total energy extracted by the system. So, for up to this point, you will get constant CP 0.5. If they basically manage to get that output power from this curve, you will have a CP like this. And once you hit that point and the power input is still increasing but the power output is constant, you will drop like this, right? And from this point on, you just basically go back to zero. So how do we come up with that CP? Output power over input power. Output power is in front of ourselves here on the graph, and the input power we get it from half rho A V cube. Okay. So the energy, which is the power multiplied by the time that stayed, the number of hours. So this is the extracted energy if you don't shut down the turbine, if you continue harvesting the energy, and if you shut it down or you slow it down on purpose, you will end up with basically this. Okay, so by making this cut out speed in your design, you end up losing all this energy, and over here you lost this much. Okay. One other concern is also in putting a wind farm, how far they should be, and the wake behind each one of those turbines takes time until it collapses basically on itself, and then you are ready to put another one. So they say 8 to 12 diameter basically, okay, so that they wouldn't affect each other, unless we are talking about those vertical wind turbines that the span from one can rotate the other one. But in horizontal one, you really need to give yourself a space to for the velocity to recover. Okay, and so if you know the initial cost that you have to pay up front, and you figure out how much energy you are harvesting every year, and you multiply that energy by 11 cents, you will be able to figure out how much money you are making every year. And so it will take you kind of 8 years or 9 years here in this graph, 10 years, for you to come up with the initial investment. So the problem with those wind turbines is that you pay upfront for everything, and then you don't get your money until it's like say 12 years, and then after 12 years you will make more money after that. Right? So it takes a lot of initial investment so that you can make your money. And those three graphs is for different. If you're getting a loan, then and that loan has higher interest rate, then it will take you even more time to pay back, because you are not paying the same amount of money, you are paying more than what you got. Right? So you are paying the initial investment and the interest as well. Right? So another reason why they are building it higher and higher, beside the economics of scale, is this table. This table is telling us that at 10 meters per second in a certain site, the velocity could be 4, but if you go 50 meters up, the velocity is 5. Here it could be 9, but you go up and it's 12. And so then it makes sense to build the turbine higher so that you can basically benefit from the boundary layer, the atmospheric boundary layer. Okay, so building it over here will harvest that velocity. By building it over here will harvest that one. And so it's a big deal because it's v cube. So we are talking about 12 cube over 9 cube. And so multiply this by 10 cent, 11 cent per kilowatt hour. Multiply this by how many kilowatt hour you're getting from a 2 megawatt that's running for 8,760. And you'll see that it's a lot of money that will pay for that tower easily to go higher. Okay, so now in the homework I'm giving you the results on that height, let's call it 10 feet, and then I'm asking you to calculate the height at say 30 feet, calculate the velocity at 30 feet. So that table, I'm giving you a table. Here is the velocity, the velocity in meter per second, and here's the hours: 20 hour, 400 hour, 800 hour, 200 hour, and say 100 hour. And all this is done at 30 feet, for example. And then if I want to go to 100 feet, that where the turbine will be installed, how does this table look like? Will I get the same velocity like what I'm getting at lower height? No, it will be different velocity, right? Those velocity will be higher. So we need to understand how do we calculate this velocity. But will I get the same hour distribution? So let's say I'll show you how we turn this 5 meter per second to, let's call it 15 meter per second. If it's 5 meter per second at that height for 100 hour per year, and I told you the calculation in the next slide will tell us, like, when it's 5 there, it will be 15 up there. How many hours will it be 15? Excellent. It will be 100. Is that clear? If it's 3 meter per second here at this height for 800 hour, and our calculation, next slide, we'll see it, that this means it's 8 meter per second at 100 feet. How many hours per year will it be 8 meter per second at the new height? 800. So we will maintain the same number of hours, but the velocity will shift. So what I'm saying is that this graph, this table, this profile will basically stay as it is for 800 hours. Okay? Down there it's 3, up there it's 8. But for how long? For 800 hours. And then for the next 200 hours it will increase, the velocity will even increase. Okay? So how do we go from one height to the other? We'll go with this equation. What this equation it say? It say uz equal uzr times z over zr to power alpha. Okay, let me rewrite this. It basically say that if you have two heights, zr and z, and you are wondering what is two different velocities, saying u over ur is z over zr to power alpha. Okay, so you go from the velocity at say 10 feet to the velocity at 30 feet by this equation. If the velocity here is 5 meter per second and you are wondering, okay, that's at lower height, what is the velocity when I go up? You just need to put 30, 10 and alpha. What's alpha? It's the train. It's this is like grass, or is it bunch of trees, or is it bunch of houses? It's urban, or is it the sea? So the train will decide what is alpha for you. Okay, so the train will decide how much is alpha. So let's use alpha 0.2. So he said the analysis believe that an average velocity is 7.5 7.5 meter per second will make the site commercially valuable. At what height will this wind speed be obtained if the wind shear value alpha is equal 0.2 is used? So he got velocity distribution, and this was done at 30 meter, and he want to see how far he need to go up so that the velocity is average velocity is 7.5 meter per second. So he need to move that table at 30 meter to different velocity, to different height. Okay, so he end up moving from 30 meter to 133 meter. Okay, from 30 meter to 133 meter. So how do you do this? So again, you write the hours over here, and here is the velocity at 30 meter, and this would be the velocity at 100 meter. Okay, and then the velocity at 200 meter, and the velocity at 300 meter. I mean, you don't really know how high I should go. You just have this table that have the hours, and it has the velocity 1, 2, 3. So to go to the velocity at 100 meter, you do this, and to go to the velocity at 200 meter, you do the same thing, and 300 meter, you do, and for every one of them, you calculate what is the average velocity until you find the right height. So how do I calculate the average velocity from that table? If I have a table like this, how do I calculate the average velocity from it? I just have hours and velocity. What's the equation that they used to calculate the average velocity? V mean was the integration of HV V dV, right? So I don't have function, so I'm not going to do integration. So if you don't have function but you have a table, you don't do integration, you do what? You do summation, right? You do summation of HV time V, right? So what is this HV? That's the number of hours multiplied by the velocity in each pen. Okay, so from 0 to 1, what's the velocity? 0. From 0 to 1, what's the velocity? 0.5. From 1 to 2, what's the velocity? 1.5. So if you multiply basically 0 times 80 plus 0.5 times 2.04 plus 1.5 times 496 plus divided by the 8760, you will come up with the V mean, and it will be as if you did the integration with the function. Okay, that is the average velocity. I had one student 1 year, guess what he did wrongly to calculate the average velocity? Yes, he added all those velocity over here, and he divided over the number of bends. Why that's wrong? Yeah, because he's assuming they're all the same fare, the same share, or like basically every one of them is the same weight like the rest. But if you have one velocity that is there for 8,000 hours out of the 8,760, that's probably the average velocity. If it's always there, right? So by multiplying the velocity time the number of hours or the probability of having that velocity, you are giving more weight to those guys. Okay?